Welcome back to Physics 192. I'm Gerard Blanchard. Last time we talked about how a changing magnetic field induces an electric field. The very last thing we need to know about electric and magnetic fields is that the opposite is also true. Just as a changing magnetic field induces an electric field, a changing electric field induces a magnetic field. And this also follows a right-hand rule. If you point your thumb in the direction of the change in the electric field, then your fingers show the direction of the magnetic field. So in other words, a changing magnetic field behaves like a current as far as producing magnetic fields. So electric fields circle around changing magnetic fields, and magnetic fields circle around changing electric fields. And these two phenomena together give us electromagnetic waves. Now just imagine for a second that I'm holding a positive charge and a negative charge, and they're right on top of one another so that they're cancel each other out, so that there's zero net charge. There's zero net charge and there's going to be no electric field. Now, if I move the positive charge and the negative charge and separate them, then there will be an electric field around them. The electric field will go out from the positive charge and converge on the negative charge. So we start off with no electric field. We separate the charges and create an electric field around them and then bring them back together. You might think that we would then have no electric fields. Well, as it turns out, that's not quite what happens. Let's take a look at this diagram. In the top row of this diagram, we start off with the situation that I described at first. All the way to the left, we have a positive charge and a negative charge very close to one another so that their charges cancel each other out and we have no electric field. In the next diagram, the second diagram from the left, we've separated the positive and the negative charges, and we have the situation that I described. We have electric field lines radiating from the positive charge and converging on the negative charge. We also have a magnetic field because we are moving the positive charge upward and the negative charge downward. That's the same as an upward current. So you can see that there are also magnetic field lines indicated. If you were to point your thumb upwards in the direction that the positive charge is moving, or in the direction of the current, then you would see that your fingers curl around that current in the same sense as the magnetic field lines curl around the two charges in the diagram. If you point your thumb up, then the magnetic field lines go into the page on the right side of the two charges and come out of the page on the left side of the two charges. In the next diagram at the top, the third diagram from the left at the top, we have the two charges moving back together this time. And you can see the electric field lines coming back together. You can also see that now, since the positive charge is moving down and the negative charge is moving up, that's the same as an upward current. So we have magnetic field lines curling around those two charges in the opposite direction to what we originally had. We have, if we point our thumb down, our finger goes into the page on the left side of the two charges and comes out of the page on the right, the same as the X's and the dots of the magnetic field closest to the two charges. In the last diagram, we have in the last diagram at the top, we have the two charges come back together, and that pinches off those electric field lines, but they don't disappear entirely. What happens is what's shown in the bottom diagram. These loops of electric field and magnetic field propagate away from the two charges, this is an electromagnetic wave. It's actually a ripple or a pulse of an electromagnetic wave. And these two loops will move outwards at the speed of light forever. Now, how is it that the electric and the magnetic fields continue to exist once we brought those two charges together? Well, they exist through electromagnetic induction. Let's take a look at the pulse on the right side of your page. As the pulse on the right side of the page moves to the right, imagine yourself at one point on the page. You would first see a negative electric field or a downward electric field, and then you would see a positive electric field. So if you were to stay at one point while this pulse passes over you, the electric field is changing in the positive direction. The electric field is changing upwards. So that's equivalent to an upwards current at the center of that pulse. So if you were to put your thumb in the upward direction at the center of that pulse, then your fingers would curl into the page to the right and out of the page to the left in the same sense that the magnetic field lines are shown. So it is the changing electric field that is sustaining the magnetic field. Similarly, the changing magnetic field is sustaining the electric field. Once again, if you were to stay still at a point on the page, you would first see a magnetic field into the page and then out of the page. So the magnetic field is changing in the outward direction, and that gives us an electric field in a loop around that changing magnetic field. So the magnetic field induces the electric field. And these two sustain each other forever as that pulse propagates outwards. That is what makes up an electromagnetic wave. A changing electric field that sustains a magnetic field looped around it, and a changing magnetic field that sustains an electric field looping around the changing magnetic field. That is why we call this an electromagnetic wave, because we need both the electric field to sustain the magnetic field and the magnetic field to sustain the electric field. They are each the medium for each other. So this, as I said, represents one electromagnetic ripple, say, the equivalent of throwing a stone into a pond and you get a ripple that propagates outwards. If we were to just move these charges up and down, it would create this ripple that propagates outwards. If we wanted a regular electromagnetic wave, then we would have to move the positive and negative charges up and down continuously. So if we were to continuously move the positive and negative charges up and down, up and down, up and down, we would generate loop after loop after loop of electric field and the corresponding magnetic fields circling around it. And these waves will propagate out forever. One wavelength of the wave would be a complete set of up and down. So I have drawn into the diagram one wavelength of the wave, where I went from one center of a circle, center of a loop, where we went from negative electric field to upward electric field, over the next loop to the third loop, where we go once again from downward electric field to upward electric field. So that represents one complete cycle of the wave. We go from zero electric field, we have a a region of positive electric field, then we go through 0 again, then we have a region of negative electric field, and we're back to 0 again. So from 0 to positive to 0 to negative, back to 0 is one wave length of the wave. And that is a fundamental characteristic of the wave. That's actually what distinguishes what type of electromagnetic wave we have. Now the wavelength, which we represent with a Greek letter lambda, that's a lowercase lambda. The wave speed, which we'll write with a v, and the frequency of the wave are all related by a fundamental equation which says that the speed of the wave is equal to the frequency of the wave times the wavelength. So the wavelength is one fundamental characteristic of the wave. Another fundamental characteristic of the wave is its polarization. The polarization of an electromagnetic wave is the plane in which the electric field oscillates. So in this case, the electric field is oscillating up and down, or vertically, so this wave would have vertical polarization. If we go back to think about the solenoid that I was using last time, it sends out electromagnetic waves, but in that case, the magnetic field was vertical and the electric field was horizontal, so the solenoid that I was using was actually generating horizontally polarized waves. Once again, the polarization is the plane of the electric field. As it turns out, the wave speed of electromagnetic waves can be calculated from our fundamental constants, K and mu naught. In a vacuum, the wave speed, v, of an electromagnetic wave is equal to a fundamental constant we'll call c, c being the speed of light. C is equal to the square root of 4 times pi times our electric constant K divided by our magnetic constant mu naught. Let's see what that works out to be. C is equal to the square root of 4 times pi times our electric constant K, which is 8.99 times 10 to the 9, divided by mu naught, which is 1.26 times 10 to the negative 6, or the speed of light is the square root of 4 times pi times 8.99 times 10 to the 9th divided by 1.26 times 10 to the negative 6, which gives me 2.99 times 10 to the 8 basic metric units, which would be meters per second. So the speed of light, which experimentally also turns out to be 2.99 times 10 to the 8 meters per second, is fundamentally related to our electric field constant, K, and our magnetic field constant, mu naught, which once again goes to show you that light is an electromagnetic wave. It is related to our fundamental constants of electricity and magnetism. So in vacuum, the wave speed of electromagnetic waves is equal to c, the speed of light, which is 2.99 times 10 to the 8 meters per second. In matter, electromagnetic waves travel more slowly, and we represent that with v, the wave speed of electromagnetic waves, is equal to the speed of light divided by a number n, where n is a number that is 1 or greater. N is 1 in a vacuum. In matter, n will be something greater than 1, so that the speed of electromagnetic waves is something less than the speed of light. We call n the index of refraction, and you'll see why later on. But that is the name of this constant n, the index of refraction. We call it an index because it's a pure number, and refraction because we need to know that when we calculate how light bends when it passes through matter. And that process is called refraction. Now, in matter, what happens is that the frequency remains constant while the wavelength changes proportional to the speed, so that the equation, wave speed is equal to frequency times wavelength, still holds, or V is equal to F times lambda. Light, radio, microwaves, X-rays, gamma rays, these are all electromagnetic waves. They all are based on the same physics of changing electric fields and changing magnetic fields. The only thing that distinguishes between them is their frequency. Here is a diagram showing you the entire spectrum of electromagnetic waves. It extends from the longest wavelengths on the left to the shortest wavelengths on the right, or the lowest frequencies on the left up to the highest frequencies on the right. Visible light is somewhere slightly to the right of middle. The wavelength of visible light extends from 700 nanometers at the longest end, I should say, or the red end of visible light, up to 400 nanometers at the shortest wavelength end, where we would find violet light. That also represents a range in frequency from 4.3 times 10 to the 14 hertz up to 7.5 times 10 to the 14 hertz. And this is the visible light spectrum is what we originally referred to as a spectrum, but it turns out that the spectrum extends on both directions. It goes on the long wavelength end, or past red on the longer wavelength side, or to the left. We go through infrared, microwaves, and then radio waves. And you can see that there's a spectrum of microwaves and radio waves that all have different uses. That's at the very bottom of your diagram. Past violet, we have ultraviolet, X-rays, and gamma rays. And once again, these are all the same phenomenon, just different frequency waves. Let's do a few exercises to get you used to these equations. Calculate the frequency of an electromagnetic wave with a wavelength the size of the thickness of a piece of paper, 60 millimeters, a 91 meter long soccer field, the diameter of the Earth, and I should tell you that the diameter of the Earth is 6,370 kilometers, or D, the distance from the Earth to the Sun, and that would be 150 million kilometers. So the diameter of the Earth is 6,370 kilometers, and the distance from the Earth to the Sun is 150 million kilometers. Okay, all of these questions are just calculations based on V is equal to frequency times lambda, where V is equal to the speed of light is equal to frequency times lambda. So the speed of light divided by the wavelength is equal to the frequency, which is what we're asked to calculate. The speed of light is 2.99 times 10 to the 8 divided by our different wavelengths is equal to the frequency. And we were asked to do this 4 different times. So I'll just do this right here. In the first case, we had A, frequency is equal to 2.99 times 10 to the 8 divided by the thickness of a piece of paper, 60 millimeters, which would be 60 times 10 to the minus 3 meters. And in that case, the frequency would be 2.99 times 10 to the 8 divided by 60 times 10 to the minus 3, and that would be 4.98 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 basic metric units of frequency, which are hertz. For B, we want to know the frequency, which would be 2.99 times 10 to the 8, for a wavelength of 91 meters. So 91. And in that case, that would be 2.99 times 10 to the 8 divided by 91. And that would be 3.29 times 10 to the 1, 2, 3, 4, 5, 6 hertz. C, we wanted to know the frequency, which would be 2.99 times 10 to the 8, where the wavelength is equal to the diameter of the Earth. I apologize. The number I gave you earlier was actually the radius of the Earth. The number I gave you was the radius of the Earth. For the diameter, we have to double that. So it would be 2 times the number I gave you, which was 6,370 kilometers. So that would be times 10 to the 3 meters. My apologies for that. This is the radius of the Earth. So the diameter would be twice that. So let's calculate that. 2.99 times 10 to the 8 divided by 2 times 6,370 times 10 to the 3rd meters. And that would be a frequency of 23.5 hertz. And finally, D, a frequency of a wave, which would be C, 2.99 times 10 to the 8, which had a wavelength equal to the distance from the Earth to the Sun, which is 150 million kilometers, so we'd have to have another times 10 to the 3 meters. And that would be 2.99 times 10 to the 8 divided by 150 million times 10 to the 3 meters. And that would be 1.99 times 10 to the minus 3 hertz. So as the wavelength gets longer and longer and longer, the frequency decreases. And those are the questions that we were asked to answer. Another question asks, what is the wavelength of the radio waves broadcast by an FM radio station with a frequency of 90 times 10 to the 9 megahertz? So this time you're given the frequency and you're asked to find the wave length of the waves. Once again, we have the wave speed is equal to the frequency times the wavelength. The wave speed is equal to the speed of light, which is equal to the frequency times the wavelength. We're looking for the wavelength now, so we would divide both sides by the frequency, and c divided by the frequency gives us our wavelength. The speed of light is 2.99 times 10 to the 8 meters per second, and the frequency was 90.9 megahertz, so that would be times 10 to the 6 hertz. That's equal to the wavelength, so we're working in basic metric units, meters per second, and hertz, so our wavelength will come out in basic metric units, and 2.99 times 10 to the 8 divided by 90.9 times 10 to the 6 gives us 3.29 meters is equal to the wavelength. So a FM radio station is broadcasting using waves whose wavelength is a few meters. Another question. Astronauts on the moon communicated with mission control in Houston via electromagnetic waves, radio waves. There was a noticeable time delay in the conversation due to the round-trip transit time for the electromagnetic waves between the moon and the Earth. How long was the time delay? And I should tell you that the distance from the Earth to the moon is 384,000 kilometers. So the distance from the Earth to the moon is 384,000 kilometers. Okay, here is the Earth. Its continents. And we send out a radio wave to the moon. And the astronauts on the moon immediately, once they hear the question, respond with a radio wave of their own. So the total distance traveled by radio waves, the question was asking for the round-trip difference. The distance is equal to twice the separation between the Earth and the Moon, which was 384,000 kilometers, so times 10 to the 3. the waves traveled at a speed v equal to the speed of light, which is equal to 2.99 times 10 to the 8 meters per second. And we can use a simple kinematic equation, or a simplified kinematic equation, to answer this. And we'll just say that the distance traveled is equal to the speed times the change in time, or the distance divided by the speed is the change in time. The distance is 2 times 384,000 kilometers divided by the speed of light, which is 2.99 times 10 to the 8 meters per second. And that'll give us our time for a wave to go here and a wave to come back. And what is that? That's 2 times 380, actually, I'm sorry, that should be 384,000. So 2 times 384,000 divided by 2.99 times 10 to the 8. And that gives us 2.57 seconds for our change in time. So for a radio wave to go from the Earth to the Moon with a question, and for the answer to come back with a radio wave from the Moon to the Earth, takes a minimum of 2.57 seconds. One last question. 2 identical television signals are sent between 2 cities that are 400 kilometers apart. One signal is sent through the air, and the other signal is sent through a fiber optic network. The signals are sent at the same time, but the one traveling through air arrives 7.7 times 10 to the minus 4 seconds before the one traveling through the glass fiber. What is the index of refraction of the glass fiber? So what we're basically looking for is we are looking for the speed of the light in the glass fiber, and we'll see that it is slowed down relative to light, and the index of refraction is that factor by which it's slowed down. Okay, here we have city A and city B. City A we'll call x is equal to 0. City B is 400 kilometers away, so that'd be 400 times 10 to the 3rd meters. And we send 2 signals from A to B. They both start out with T initial is equal to 0. This signal travels through the air, and so V air would be equal to the speed of light, which would be equal to 2.99 times 10 to the 8 meters per second. And then another one travels through a cable and through a fiber. So we'll call that VF for V fiber. And we don't know. And that's what we're looking for. T final for the air, we don't know. T final for the fiber, we are told is T final in the air plus 7.7 times 10 to the minus 4 seconds. We were given that. We were told that the signal in the air arrives first. The signal in the fiber arrives 7.7 times 10 to the minus 4 seconds later. Okay, what can we do here? We know the speed in the air. We can use that to calculate T final in the air. From T final in the air, we can find T final in the fiber. And with T final in the fiber, we can calculate the speed of the wave in the fiber. And from that, we can calculate the index of refraction, because V fiber is equal to C divided by the index of refraction in the fiber. And it's this in fiber that we're looking for. Okay, let's do that. X final minus X initial is equal to V air times T final in the air minus T initial, or 400 times 10 to the 3 minus 0 is equal to 2.99 times 10 to the 8 meters per second times T final in the air minus 0, or 400 times 10 to the 3 divided by 2.99 times 10 to the 8 is equal to T final in the air. And what is that equal to? That is equal to 400 times 10 to the 3 divided by 2.99 times 10 to the 8. That is equal to 1.34 times 10 to the minus 3 seconds is equal to T final in the air. So the signal in the air takes 1.34 milliseconds to get from city A to city B. Okay, that's our first step. We found T final in the air. Next, T final in the fiber is equal to T final in the air plus 7.7 times 10 to the minus 4 seconds. We were told that. So T final in the fiber is equal to 1.34 times 10 to the minus 3 plus 7.7 times 10 to the minus 4. Our T final in the fiber is equal to 1.34 times 10 to the minus 3 plus 7.7 times 10 to the minus 4. And that is 2.11 times 10 to the minus 3. So the signal through the fiber took 2.1 milliseconds, times 10 to the minus 3 seconds is a millisecond, to get from A to B. From that, we can use our kinematic equation again. X final minus X initial is equal to V in the fiber times T final in the fiber minus T initial. And so we have the same thing. We have 400 times 10 to the 3 minus 0. That's X final minus X initial is equal to V fiber times 2.11 times 10 to the minus 3 minus 0. And that tells us that 400 times 10 to the minus 3 divided by 2.11, I'm sorry, that should be 400 times 10 to the 3, 10 to the positive 3. 2.11 times 10 to the minus 3 is equal to the speed in the fiber, or 400 times 10 to the 3 divided by 2.11 times 10 to the minus 3 is 1.89 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 is equal to the speed of the signal in the fiber. Okay, and finally, let's come back up here, and we will use V fiber is equal to the speed of light divided by the index of refraction in the fiber. We can solve that for the index of refraction in the fiber. N fiber is equal to C over V fiber, or N fiber is equal to 2.99 times 10 to the 8 meters per second divided by V fiber, 1.89 times 10 to the 8, or N fiber is equal to 2.99 times 10 to the 8 divided by 1.89 times 10 to the 8 gives me 1.58, and it is a pure number because we have meters per second divided by meters per second. So the index of refraction of the glass fiber is 1.58, which means that the speed of the wave in the fiber is the speed of light divided by 1.58. So, electromagnetic waves exist through the interaction of electric fields and magnetic fields. The changing electric field induces the magnetic field. The changing magnetic field induces the electric field, and so on and so forth as the wave propagates forever. Light, radio waves, X-rays are all forms of electromagnetic waves. They only differ in their frequency. The frequency of these waves times their wavelength equals the speed of the wave. And the speed of electromagnetic waves in vacuum is equal to the speed of light, which we can calculate from our fundamental electric constant and magnetic constant. In matter, these waves travel more slowly. They are slowed down by matter by a factor that we call the index of refraction. And from here, we're going to focus on that. We're going to focus on the interaction of light waves with matter, and that gives rise to the field of optics, which we'll talk about next time. Until then, think physics.